Welcome to the lecture series on CFD, Part 1. This is Lecture 6 on application examples for finite difference methods and error analysis. Higher order finite difference methods require special treatment near boundaries. That will be the first topic of this lecture. The next topic is the implementation of Dirichlet and Neumann boundary conditions in finite difference methods, followed by a description of methods for error estimation and grid dependence analysis. The finite difference methods described in lectures 4 and 5 are then applied to two test cases. One is a one-dimensional test case with an exact analytical solution so that errors can be directly computed. The other test case is two-dimensional with an analytically defined velocity field. Grid dependence studies were performed with schemes of orders from first to fourth, also with schemes of different order applied to convection and diffusion terms. Higher order approximations refer to more distant neighbor nodes like I-2 and I+2. Such neighbors do not exist near boundaries. At grid node I equal 2, there is only one neighbor node to the left, the boundary node I equal 1, as shown in this figure. The problem can be solved in two ways. One is to create ghost nodes outside solution domain, as shown in this figure. One can then use standard approximations for derivatives at node I equal 2, but variable values at the ghost nodes must be obtained by extrapolation using, for example, polynomial fitting through the boundary node and a certain number of internal nodes. If polynomial fitting is used to derive approximations for derivatives, it is best to use the same polynomial to extrapolate to ghost nodes. The other approach is to use different approximations for derivatives at the next two boundary nodes. They should be of the same order as at other internal nodes, but asymmetric. An example is shown in this figure. A polynomial of degree 4 is fit to variable values at 5 nodes, and its derivatives at node I equal 2 are used instead of the regular expression which is used at nodes I equal 3 and I equal 4, and so on. Examples of both approaches are shown in the next two slides. Here are examples of extrapolation to ghost nodes for third and fourth order polynomial fits. From a polynomial of degree 3 fit to variable values at the boundary node and 3 inner nodes, one obtains on a uniform Cartesian grid the following expressions for variable values at ghost nodes. From a polynomial of degree 4 fit to variable values at the boundary node and 4 inner nodes, one obtains on a uniform Cartesian grid the following expressions for variable values at the ghost nodes. With variable values at ghost nodes computed in this way, standard expressions for derivatives at nodes I equal 2 and I equal n-1 can be used. As explained in lecture 5, higher order schemes are usually implemented using the third correction approach. In this case, the explicit computation of variable values at ghost nodes is not a problem because one computes then explicitly the difference between complete derivative approximations of high and low order. Here is an example of using different expressions for derivative approximations at near boundary nodes based on a polynomial of degree 4 fit to variable values at the boundary node and 4 inner nodes. On a uniform Cartesian grid, the following fourth order asymmetric approximations of first and second derivative at node I equal 2, shown in this figure, and at node I equal n-1 are obtained. This makes the programming a bit more complicated. For the sake of completeness, I show in this and the following slide how to derive the coefficients for a polynomial of degree 4 fit to variable values at 5 nodes and how to use the polynomial to obtain expressions for derivative approximations. This is the expression for the polynomial of degree 4 with its 5 unknown coefficients. The local coordinate system is centered at node I, thus A0 equals phi I. These four expressions define polynomial at nodes I-2, I-1, I+1 and I+2. They contain 4 unknown coefficients. These coefficients can be determined in the following way. First, we sum the framed expressions. The terms involving coefficients a1 and a3 cancel out, and we obtain two equations with two unknowns, a2 and a4, which are easily solved. Next, we subtract the framed equations. Now the terms involving coefficients a2 and a4 cancel out, and we obtain a set of two equations with two unknowns, a1 and a3, which is also easily solved. Upon solving the equations from previous slide, the following expressions are obtained for the remaining four coefficients of the polynomial. When the polynomial fit is performed around the node I equals 3, we can obtain with these coefficients the expressions for derivatives at nodes I equal 1 and I equal 2, and for the variable value at the ghost node I equals 0 shown in preceding slides. The same applies when the polynomial fit is performed around node I equal n minus 2. We can then, with these coefficients, obtain the expressions for derivatives at nodes I equal n and I equal n minus 1, and for the variable value at the ghost node I equal n plus 1. We need to apply finite difference approximations to all derivatives featuring in the differential equation at every inner node. However, at boundary nodes, we must know something about the solution to be able to solve the resulting system of algebraic equations. Usually, one of these two options are valid. We know the variable value at the boundary node. This is called Dirichlet boundary condition, named after German mathematician Johann Peter Gustav Lejeune Dirichlet. Or we know the gradient of the variable in a particular direction at the boundary. This is called Neumann boundary condition, named after German mathematician Karl Gottfried Neumann. If the boundary value of the variable is not known, we use the gradient condition at the boundary node to obtain the boundary value from inner nodal values. Examples are shown in the next slide. In finite difference methods, derivatives at boundaries are normally not required, except when compact schemes like Padé schemes described in Lecture 5 are used. However, we may need to compute the gradient at a boundary for post-processing reasons, for example to compute the heat flux or shear force. When the boundary value of the variable is specified, we can compute the derivative at the boundary from one-sided approximations as described in slide 8. In the same way, one can compute the boundary value of the variable when the gradient is specified. Here are two examples. Two more are described at the next slide. If we assume a linear variation of the variable, this is the approximation of the first derivative at the boundary, the forward difference, using variable values at nodes 1 and 2. If the derivative is prescribed, we obtain the boundary value like this. If we assume a quadratic variation of the variable, this is the approximation of the first derivative at the boundary using variable values at 3 nodes, 1, 2, and 3. If the derivative is prescribed, we can compute the boundary value using this expression. If we assume a cubic variation of the variable, this is the approximation of the first derivative at the boundary. It uses variable values at 4 nodes, 1, 2, 3, and 4. If the derivative is prescribed, we obtain the boundary value from this expression. Finally, if we assume a polynomial of degree 4, this is the approximation of the first derivative at the boundary using variable values at 5 nodes, 1, 2, 3, 4, and 5. Again, if the derivative at the boundary is prescribed, we can obtain the boundary value from this expression. At every inner grid node, we write an approximation of the transport equation based on finite difference approximations of derivatives. There results one algebraic equation per inner grid node, in which the variable value at that node, here denoted with subscript p, and at several neighbor nodes are unknowns. All terms that contain only known values are grouped together on the right-hand side as qp. Note that when deferred correction approach is used to implement higher order schemes, qp also contains the explicitly computed difference between high order and low order approximations of derivatives, while the coefficients ap and al are based on the low order approximation. With the deferred correction approach, usually only the nearest neighbors of node P are included in the sum. We then say that the computational molecule looks like this in 2D, or like this in 3 dimensions. Without the third correction, the computational molecule in 2 dimensions may look like this. For the solution domain as a whole, a matrix equation is obtained, where phi is the vector of unknown variable values at all linear grid nodes, q is the vector of the source or sink terms, qp in the above equation, and A is the sparse coefficient matrix. With structured grids, we usually use the so-called lexicographic ordering of grid nodes, which results in a diagonal structure of the coefficient matrix, as shown in this figure here for a 5 by 5 nodes 2-dimensional grid. This table shows the conversion between grid indices I, J, K, the compass notation P for center, W for west, S for south, N for north, E for east, B for bottom, and T for top. And the possible storage notation is used in most sample codes that I am providing. Here, Ni is the number of nodes in I direction, including boundary nodes, etc. In this case, nodes are ordered from south to north along lines of constant index I, starting at the west boundary and proceeding line by line toward east boundary. In 3-dimensional problems, this is first done on the bottom boundary, proceeding plane by plane toward top boundary. Note that in this coefficient matrix, the elements of the AW diagonal are missing for the first row of inner nodes. It is assumed that boundary values are known and the product of AW times phi W is put to the right-hand side in QP. The same is true for the last row and AE diagonal. AS diagonal misses an element at all nodes next to south boundary, and AN diagonal misses an element at all nodes next to north boundary. Methods for solving such equations will be presented in lectures 10 to 12. The discretized equations are based on finite difference approximations of derivatives and thus represent only approximations of the original partial differential equations. The exact solution of the partial differential equation, if we could solve it analytically, would not satisfy the discretized equations at any grid node. The imbalance is the truncation error, resulting from truncation errors in all approximations. This operator represents the partial differential equation, and the capital phi is the exact solution. The operator LH represents the discretized equation on a grid with spacing h. Tau h is the truncation error on grid with spacing h. The exact solution of the discretized equations on a grid with spacing h satisfies this equation. The difference between the exact solution of the partial differential equation, capital phi, and the exact solution of the discretized equation on a grid with spacing h, phi h, is the discretization error on that grid. For linear problems, the following relation holds. This means that a discretized equation for discretization errors looks the same as the discretized equation for the variable phi, only the right-hand side is different. Here, the negative of the truncation error. Because the conservation equations are in general non-linear and the truncation error is never known, this equation is not of a great value. However, we shall see in the next lecture series how it can be used to estimate discretization errors and thus guide local error-guided grid refinement. When the grids are sufficiently fine, the leading truncation error terms in approximations are dominant, and we can express the discretization error as a function of grid spacing to power p. The unknown coefficient alpha is not important because at a given location it does not depend on grid spacing. With this assumption, we can express the exact solution of the partial differential equation as the solution of the discretized equation on a grid with spacing h plus the discretization error estimate on that grid plus higher order truncation error terms. This can also be done for a grid with twice or 4 times larger grid spacing, 2h or 4h. Assuming a monotone convergence, which is a reasonable thing to do when the last 3 grids are sufficiently fine, we can estimate the overall order of approximation for the complete discretized equation as follows. It is useful to use this expression to check the computer code on a test case where sufficiently fine grids can be afforded to make sure that the order comes out as expected. If you programmed 4 order approximations, but this expression returns a value around 2, you know that there is a programming error somewhere. Also, if you use approximations of different order for first and second derivatives, this expression will normally return the lowest order of the 2 approximations used. When the order is known, we can estimate the discretization error from solutions obtained on the finest grids. From these expressions, one can easily derive the expression for the discretization error on the grid with spacing h, the finest grid. It is equal to the difference between the solutions on the 2 finest grids divided by this factor. So far, it was assumed that grid spacing was halved, that is, the refinement ratio was 2. The analysis, which is known as Richardson extrapolation, is valid also for different refinement ratios. Just replace 2 by the refinement ratio R. You will find in literature more sophisticated methods accounting for non-monotonic convergence and other specialties, but they all follow a similar approach. Let us now solve one-dimensional transport equation involving convection and diffusion of a generic scalar variable phi with Dirichlet boundary conditions at both ends. A reasonable physical experiment would be a fluid flow through a long pipe with a constant temperature T0 up to x equals 0, a perfectly insulated section of length L, and then again maintaining a constant temperature TL. The experiment would not be easy to realize, but it helps to understand what is involved. Such problems in which convection is balanced by diffusion in streamwise direction are seldom, but this example has one nice property. The partial differential equation has an analytical solution given by this expression. Here, PE is the Peclet number defined by this expression. It looks the same as the Reynolds number when dynamic viscosity is replaced by the diffusion coefficient gamma. These are the values of other parameters. For the Peclet number equal to 0, there is no flow and we have a pure diffusion. In that case, the steady state solution is a linear variation of phi. When convection dominates, the effect of diffusion is felt over a shorter distance and the variation of phi becomes locally more sudden. 4 approximations of the first derivative, that is convection term, we used. First order backward, called up indifferencing, second order central differencing, third order backward, and fourth order central differencing. For the second derivative, that is diffusion term, second order or fourth order central differencing was used. Asymmetric approximations are practically never used for diffusion terms. With the known analytical solution, we can define the error norm as follows, and by conducting a systematic grid refinement, show how the numerical solution converges toward the analytical solution, which is now the true grid-independent solution. The plot on the left shows computed profiles of phi when the first order backward scheme is used for convection and second order central difference scheme for diffusion. The plot on the right shows the same information when the second order central differences are used for both convection and diffusion term approximations. Shown is only the segment from x equal 0.8 to 1 because at the resulting Peclet number of 50, the diffusion transport does not propagate further upstream. Phi approximately 0 prevails from x equals 0 to x equals 0.8. We see that the choice of approximation for convection term plays an important role. The first order upstream scheme results obviously in a strong numerical diffusion. On coarse grids, the obtained profile of phi corresponds to the exact solution at a much lower Peclet number. On the other hand, the use of second order central difference approximation for convection causes oscillations with strong undershoots when grids are coarse. These are called dispersion errors. The solution for 10 subdivisions is not shown, it looks much worse. These problems disappear when the grid is refined so that the Peclet number based on grid spacing instead of domain length L is smaller than 2. The refinement could be local, only where the slope of the profile varies a lot. Grid Peclet number can be larger where the profile is nearly linear. The plot on the left in this slide shows computed profiles of phi when the third order backward scheme is used for convection and the fourth order central difference scheme for diffusion. The plot on the right shows the same information when the fourth order central differences are used for both convection and diffusion term approximations. The third order backward scheme also produces undershoots on the coarser grid, but from 40 subdivisions onward, the result is close to the analytical solution. When the fourth order central differences are used for both convection and diffusion, there are no undershoots in solution, but on the coarser grid, the errors are obviously large, while from 40 subdivisions onward, the result is close to the analytical solution. This slide shows the distribution of local error in solutions obtained with different combinations of approximations for convection and diffusion terms. Left for the grid 2 with 40 subdivisions and right for the grid 5 with 320 subdivisions. Negative error means that computed values are greater than the exact solution and vice versa. For both grids and all scheme combinations, errors are the largest around the location x equals 0.98, which is where the strong change in profile slope begins. Errors are negligible for x less than 0.8 for all schemes. The first order scheme for convection results in by far the largest errors. Differences between second order and fourth order schemes are much smaller than the difference between first order and second order scheme. This slide contains very important information which is valid for many, if not most, flow problems. We'll check this in future test cases to make sure that the conclusions still hold. The important conclusion from this diagram, which shows the variation of error norm defined in slide 16 with reducing grid spacing for various scheme combinations, is the overall convergence order corresponds to the lowest order of approximations used for convection and diffusion terms. We have 4 unequal orders of approximations for convection and diffusion terms to be sure that the outcome is not accidental. First order for convection, second order for diffusion, UD1, CD2. Third order for convection, second order for diffusion, UD3, CD2. Third order for convection, fourth order for diffusion, UD3, CD4, and fourth order for convection and second order for diffusion, CD4, CD2. In addition, we have results from pure second order, CD2, CD2, and pure fourth order, CD4, CD4 approximations. When the first order approximation is used for convection, the error reduces by 1 order of magnitude when the grid spacing is reduced by the same factor. It does not help that the diffusion is approximated with second order. On the other hand, if we stick with second order approximation for diffusion term, it does not help to go to third order or fourth order with the approximation of convection term. The convergence will still be second order. It is probably accidental that the errors are the same for all 3 combinations in which second order is the lowest. In most cases, the error values will be different, but the slope of the line will be eventually the same. The third order for convection brings only benefits over second order approximations if diffusion is also approximated with at least third order. The highest accuracy is obtained when the fourth order central differences are used for both convection and diffusion. The errors are reduced by 4 orders of magnitude when the grid spacing is reduced by 1 order of magnitude. On the finest grid, the error norm is more than 3 orders of magnitude smaller than when second order schemes are used, and more than 5 orders of magnitude lower than when first order upwind scheme is used. Let us now consider another more realistic test case. We want to solve the generic scalar transport equation shown here with a known but non-trivial velocity field. Such a velocity field is offered by a so-called stagnation point flow, an viscid flow defined by u equal x and v equal minus y. The following boundary conditions are specified: 0 values of phi at inlet, 0 gradient of phi at outlet, prescribe linear variation of phi along west boundary from phi equal 1 at y equals 0 to phi equals 0 at y equal 1, and zero gradient of phi in y direction at the south boundary, which is a symmetry condition. The main quantity of interest is the diffusion flux of phi through the west boundary. If phi were temperature, this would correspond to heat flux along an isothermal wall. Both the integral value, that is the total flux through the west boundary, and the local variation of flux per unit area are computed on systematically refined grids using various discretization schemes. Note that fluxes are not part of the solution process in finite difference methods, as is the case in finite volume methods. Here the fluxes need to be computed in a post-processing step. To be consistent with the solution process, gradient of phi at the west boundary needed to compute the flux is obtained using approximations of the same order as the dominant order of the overall discretization, as described in slides 10 and 11. The plot on the bottom shows an example of computed lines of constant phi. The plot on the left shows the computed variation of diffusion flux, that is the product of diffusion coefficient and the first derivative of phi in x direction, when the first order backward scheme is used for convection and the second order central difference scheme for diffusion. The plot on the right shows the same information when the second order central differences are used for both convection and diffusion term approximations. Computations are performed on 6 uniform grids, the grid spacing being halved with each refinement. Based on the experience from the first test case, we expect to see first-order convergence when the first-order upwind scheme is used for convection terms, even though diffusion terms are approximated using second-order central differences. This would mean that the distance between curves obtained on successive grids is halving, but it looks worse than that. Only for grids finer than 80 by 80 subdivisions we can observe such a tendency. The situation is better when second-order central differences are used for both convection and diffusion. The first grid is obviously too coarse, but from 40 by 40 subdivisions the expected reduction of distance between curves by a factor of 4 is evident. By comparing the peaks on the curves, we see that the solution from the finest grid in the left plot is less accurate than the solution from the 160 by 160 subdivisions in the right plot. In this slide, the plot on the left shows the computed variation of diffusion flux along the west boundary when the third-order backward scheme is used for convection and the fourth-order central difference scheme for diffusion. The plot on the right shows the same information when the fourth-order central differencing scheme is used for both convection and diffusion term approximation. We see immediately the solutions obtained using high-order schemes are much more accurate than solutions obtained using first- and second-order schemes. The solutions from the 3 coarsest grids differ significantly, while solutions from the 3 finest grids cannot be practically distinguished from each other in the plot. Here we compare solutions from 4 schemes obtained on the grid with 160 by 160 subdivisions. The first-order upwind scheme leads obviously to 2 large errors. The solution obtained with second-order central difference scheme is much more accurate. The third-order upwind scheme for convection together with fourth-order central difference scheme for diffusion is more accurate than the second-order scheme. But the difference between the two is about 8 times smaller than the difference between first and second-order schemes. Finally, the use of the fourth-order central differences for both convection and diffusion leads to the most accurate solution. Here we are looking at the total diffusion flux through the west boundary. The local heat flux per unit area at the boundary grid nodes was integrated along the whole boundary using the fourth-order Simpson rule for all schemes. The plot on the left shows how the total heat flux varies with reducing grid spacing. The high-order schemes converge rapidly toward grid-independent solution, while the solution from the first-order scheme still contains a large error even on the finest grid. Estimation of grid-independent solution using Richardson extrapolation and the assumed order, second for CD2 and fourth for CD4, leads to the same value on 5 more significant digits when applied to solutions from second and fourth order central differences, minus 1.26169 and minus 1.26166 respectively. The error estimates for each scheme and grid were computed using the above estimate of grid-independent solution. They are shown in plot on the right as a function of grid spacing on a log-log scale. The first order scheme leads asymptotically to slope 1. The error reduces 1 order of magnitude when the grid spacing is reduced by the same factor. The fourth order scheme approaches asymptotically slope 4, which is shown by extending the slope from the solutions obtained on the two finest grids. This means that with further grid refinement, the error would fall 4 orders of magnitude when the grid spacing is reduced by 1 order of magnitude. If the aim is to obtain a solution with an error below 1%, CD4 and UD3 achieve this on a 160 by 160 grid, CD2 requires 320 by 320 grid, and UD1 would require more than 5000 by 5000 grid. Let me now briefly summarize this lecture. We have seen that high-order approximations require special treatment near boundaries. One can use either asymmetric polynomial approximations at the next to boundary nodes or create ghost nodes outside solution domain. To obtain variable values at ghost nodes, extrapolation from inside is required. Both approaches lead to the same solution. When the solution exhibits sudden changes in profiles, as in the one-dimensional test case, central differences lead to oscillations on coarse grids. This is dispersion error. First-order upwind scheme produces too much numerical diffusion, and its solutions are not accurate even on very fine grids. If approximations for convection and diffusion terms are of different order, the solution converges with the lowest order used in the discretization process. The fourth-order central differences for both convection, that is first derivative, and diffusion, that is second derivative, lead in both test cases to the most accurate solutions.